So, ordinal data is it's just things that are in order. There's no different a sense in which the magnitude is captured with just no first, second, third, big, biggest, smallest. So again, means make no sense here. So using things like medians or something like that is an appropriate way of representing these data. Interval data this is where things start to become more like the kind of numerical things that you are probably more familiar with. This is similar to ordinal data, except the actual distances between the items is actually given and specified. And this is kind of important because we can actually say now that the difference between, for example, 10 degrees Celsius and 20 degrees Celsius is a fixed amount, namely 10 degrees Celsius. And we know that that distance is exactly the same as the distance between 40 degrees and 50 degrees. Okay, so we can really kind of start to use real numbers now to represent the way that the world is. But there's no true zero in this particular case. So these forms of measurement, zero doesn't necessarily mean zero. In other words, an absence of whatever it is you're measuring. So 0 Celsius does not mean no temperature at all. It's not the coldest you could possibly get. We know that because we have -10, -40, and so on. So the 0 doesn't necessarily mean 0. So it's important to attend to this. Something like absolute 0, Kelvin temperature, in that case 0 actually means 0. It means no temperature whatsoever. Okay, so this also means that 20 degrees is not twice as hot as 10 degrees. Because there's no, because 0 doesn't necessarily mean 0. But the important thing about this is that you can use the mean and the standard deviation, which we'll be looking at later, in order to represent these forms of data. The final one is ratio data, and in ratio data, it's exactly the same as for interval data that we just saw, but there's a true 0 here. So in this particular case, we know that 0 seconds, for example, means no time at all, 0 meters means no length at all, 0 kilograms means no weight, and so on. So different from Celsius, in that 0 actually means an absence of whatever it is you're measuring. And this also has the benefit of when we say 2 kilograms, we know that 2 kilograms is exactly twice as much as 1 kilogram, and 10 minutes is twice as much as 5 minutes. And again, as for interval data, we can use means and standard deviations. So a way of remembering these different kinds of data is NOIR, nominal, ordinal, interval, ratio. And interval and ratio are the kind of minimal requirements. Interval is the minimum you can actually use, makes sense to use means on. It's the minimum kind of data in order to use parametric statistics on, so things like t-tests and Pearson correlations and analysis of variance and regressions and all these things. You need at least interval data. You can also do it with ratio data, but you cannot use these tests, nor does it make sense to use means and standard deviations with data at the nominal or ordinal level. So there's a line between the O and the I in the NOIR, which is the minimal requirement for what's so-called parametric assumptions. The data need to be interval or ratio. That's your first step in determining the kind of test you can do, and the first test to establishing whether you can use the data to meet parametric assumptions. So, already said this already. So let's look at some of these ways of summarizing data. We know means, medians, modes. I'll cover these again, at least some of these. And not only are we interested in measures of central tendency, but also measures of dispersion. Let's look at what this means in a bit more detail. Here's two groups of numbers, which might be two particular treatment conditions in an experiment. What we want to do when we get a bunch of numbers is to try and capture the numbers that you have in a kind of easy to handle way. And probably the most straightforward way of doing is to use a mean. A mean, I'm sure you all know what that means. You add all the numbers up and divide by the number of numbers, and then you get a number which is hopefully represents the typical score, or if you like, the typical person. And if we look at this, the mean on the left group is 13.4, and that kind of is similar to a lot of the numbers in there. There's a 13, in fact, there's two 13s. There's a 12, there's a 14, there's a 16. There are a few numbers which are a little bit above the 13, like 9 and 19, but 13.4, if you were saying, what does the average person like in this particular group? Well, there are 13.4. It captures it reasonably well. That's a relatively good way of capturing a typical score, the typical person. And for the other group, we can look there, it's 11.6, and again, there are some 11s and some 10s, there's a 13 in there. Again, it's pretty typical. It doesn't capture everybody, but that's not the point. It's trying to give you an idea of the typical person. We can see that typically, in the left-hand bunch of numbers, people are scoring higher on whatever measurement it is than in the right-hand measures. That again tells us something about the difference. However, there are other forms of summary. We've got two sets of scores here, 4, 4, 5, 6, 6, 7, 10, and 1, 1, 1, 1, 12, 13, 13. And if we find the average of these, find the mean of these, we end up with 6. And that's may or may not be a nice typical way of capturing the numbers there. But there's something missing. What we're not getting a feeling of here, we're getting a feeling for the similarity of all these numbers, the typicality, but we're not getting a feeling for the diversity. So we need to try and find ways of capturing the diversity. The most obvious one is the range, in which we simply find the biggest number and take away from that the smallest number, and that gives us some sense of capturing the diversity of scores in there. So 10 minus 4 for the first one, it gives us a range of 6. 13 minus 1 is 12. So we give a mean of 6, gives some idea of how the typical person, and the range here has given us some range of the diversity of scores, and we can see that in that second group of numbers there is more diversity, and that is represented in the bigger range of 12. There is another measurement which is similar to that, which is called the interquartile range, and I'll let you read this slide, which you can get from Blackboard. There's stuff on this on the website as well, which you can find a link to the website on the in topic 4 in the topics area of the IRM Blackboard site. But the interquartile, I'll just mention this very briefly. Basically what the interquartile range does, it gets the range of numbers, it puts them in order from smallest to biggest. It finds the middle number, so that's then them, and kind of, if you like, imagine it's a kind of sausage or something, cut it in the middle. So now we've got the upper 50% and the lower 50% of the numbers. If what we then do is to cut those two in half, okay, so now we've got 4 items. We've got the lower quarter, the middle quarter, the third quarter, and the upper quarter. We take the end quarters away. We take the lowest quarter away and the biggest quarter away. Then what we end up with between the lowest quarter, now the lowest half and the upper half, is the interquartile range. So the interquartile range is essentially all the numbers lined up in order with the top quarter and the bottom quarter taken off, and we're simply looking at that. Now the advantage of this is that this tends to make the range less sensitive to extreme outliers. For example, if you've got a very, very big number or a very, very small number, atypically big or atypically small, then using the range can make the scores look much more diverse than they really are, simply because these big numbers are dragging the range up or down. So what the interquartile range does is chop the top bits off the full range and just deal with the middle 50%, and that makes it less sensitive. The only reason I mention that is because they are used in box plots, which we'll see later. The standard deviation, however, is probably the most widely used and familiar of these measures of dispersion. Again, we've got some numbers here. One of the things that the standard deviation does is to try and find the average deviation. Now, if you think about what the average does, the mean average does, it simply adds all the numbers up and divides by the number of numbers to find the mean. Now, what we really like to be able to do is to say, let's find the mean of this top bunch of numbers, which I think we know is 6, and let's look at how each of the other scores deviates from 6. So we can look at the first one, which is 4, and we say, oh, well, that's minus 2, because it's 2 below the mean. The next one is minus 2 again, because it's 4, again, 2 below the mean. The next one is minus 1. The 6, well, that's exactly the same as the mean, so that deviates from the mean 0, so we get 0 and 0. Then 7 is plus 1 above the mean, so that's 1. And 10 is plus 4 above the mean, so that's plus 4. So what we'd have there, in terms of the deviation scores, how much each of these individual scores deviates from the mean, would be minus 2, minus 2, minus 1, 0, 0, plus 1, plus 4. What we'd like to do is to add those numbers up and divide by the number of numbers, and that would give us an average deviation score, just in the same way that the mean gives us, an average score of the typical person. The trouble with that is when you add those numbers up, you always end up to 0, right? So minus 2 plus minus 2 is minus 4. Minus 4 plus minus 1, which is the 5, gives us minus 5. 0, 0, they don't count, so minus 5. Oh, we've got a plus 1 there, so if we add plus 1 to minus 5, we get minus 4, and then the 10 is 4, so 4 plus minus 4 is 0. So when you look at the deviation scores, they always add up to 0, so we can't divide that by the number of numbers because that's not an impossible calculation. So what we can do here is to try and stop these negative numbers from happening. And the simplest way to do that is if you multiply each number by itself, or each deviation score by itself, then you end up with a positive number. So again, minus 2, well, let's square that. Minus 2 times minus 2 is plus 4, and so on. So you can see that what you end up with there is a number where suddenly we get rid of all the negatives. So we end up with a nice positive integer, which we can now divide by the number of numbers. Okay, so that's basically what the standard deviation does. It looks at the average deviation of each score from the mean, but in order to do that we have to square each number to try and get rid of those negative numbers. We add those together, but the trouble is when we've squared these numbers, we end up with a very big number. You know, it ends up being 4 plus 4 plus 1 plus 0 plus 0 plus 1 again plus 16. We get a very big number. So that big number is, we want to kind of reduce that down so it actually works out as being something more manageable. So the way of doing that is to reverse the effect of all those squarings. So we simply find the square root of it. So let's look. I'm not a huge fan of putting equations up, but I like this equation. Put this equation up because it simply demystifies it. What we have here, let's look at this one here. We simply say, this one on the left here, standard deviation. Well, it's each number minus the mean. Right, so we take the mean away from each number. Now to get rid of those negative numbers, we simply square it, as we saw. So we produce a list of these numbers all squared, then the sigma means we add each number to each other number, so we add all the numbers up. Then we simply divide by the number of numbers, and when we've divided by the number of numbers, we have a very big number, so what we do is we find the square root of it to make it more manageable. Okay, so I want to try and demystify the standard deviation. It is sensible, it is a very useful thing, and the equation can sometimes make it more complicated than it looks, but actually it's a very sensible thing. So when we look at this, SPSS does all this stuff for you magically. You don't have to work with these equations, but it's just to give you a feel for what's going on. Then we get, for the first set of numbers, a standard deviation of 2.1. For the second set of numbers, a standard deviation of 6.2. Again, this kind of standard deviation captures the diversity of scores, whereas the mean captures the kind of typicality of the scores. The first one says, what does a typical person look like, or what does a typical score look like? The standard deviation says, well, how diverse is this group? And really important, when looking at data, people always look at the means. Are the means different? Have a look at the standard deviation, because sometimes it's important to find out that one group might be much more diverse than the other. That might lead you to think, well, why is it? Why is one more group more diverse than the scores are given than the other? That might be a useful thing to start to think about if you're criticising other people's research, or indeed you're analysing your own data.